Assalamualaikum. We are from group number 1 from section 5, and today we are excited to present our project which explore the fundamental principle of mathematics and their practical applications. We are in a group of 5 members. I am Nurul Atika Shazwana, and the other members' name is Siti Nurranisa Najwa, Nur Badariah Aina, Muhammad Azizi, and Muhammad Abdul Hakim. Today we will be focusing on two primary types of mathematical sequence, which is arithmetic sequence and geometric sequence. First, what is arithmetic sequence? Arithmetic sequence is a sequence where the difference between any two consecutive terms is constant. And for geometric sequence is a sequence where the ratio between any two consecutive terms is constant. Piston rod problem is about how heat affects engine parts. When the engine runs, the rod gets hot and expands. When it's cool, it shrinks. This constant seesawing can cause the rod to physically strike other parts if the design clearance is wrong. Eventually, the metal gets tired, what we call thermal fatigue, and can actually break or fail completely. The problem is how can we model piston rod expansion using arithmetic and geometric sequence, and when does the rod become unsafe? Objective of the study is first to apply arithmetic sequence in predicting piston rod expansion. Second, to apply geometric sequence in predicting piston rod expansion. And lastly, to compare results and discuss which model better represent in real-world behavior. For methodology, we calculate using formula of arithmetic sequence and geometric sequence. We are given the specific value of parameter, which is initial rod length equal to 100 mm, constant increase in length per cycle 0.8 mm, maximum safe rod length equal to 112 mm, growth ratio equals to 1.008 mm, and lastly, cycle number. For step of calculation, we use two types of calculation, which is manual calculation and Excel calculation. For manual calculation, we need to identify given value. List A1, D, R, and M clearly. Second, we need to apply formula. Use the formula above to calculate T50 or the extension at cycle 15 and S15, the total extension at cycle 15. Third, we need to determine average. Divide S15 by 15 to find the average expansion per cycle. And lastly, solve for n. We arrange the Tn formula to find the smallest integer n, where Tn greater or equal to m. And for Excel calculation step, first we need to create column. Set up column for cycle n, arithmetic Tn, arithmetic Sn, geometric Tn, and geometric Sn. And then secondly, we need to input the formula for arithmetic and geometric. And lastly, we need to autofill. We need to drag the formula down to complete the table for 20 cycles. Question: we need to using Microsoft Excel to visualize the data trends. So first we need to select the cycle n column and the corresponding Tn or Sn columns for both model. Secondly, we need to insert a scatter with a straight lines chart to show the growth curve. Third, we need to manually add a constant data series at y equals to 112 to represent the maximum safe limit. And lastly, we need to labels for the x-axis and y-axis are added for clarity.
So for my part, I'll be explaining about part A, the arithmetic sequence. So for the first question, the formula for n term is Tn equals to A plus bracket n minus 1 close bracket times by D, and the formula for sum of first n terms Sn is bracket 2a plus bracket n minus 1 close bracket d and close bracket. So for the second question, we'll be going to extension at cycle 15, which is T15. So it is equals 100 plus bracket 15 minus 1 close bracket, and then open bracket times by 0.8 and close bracket. Then it will be simplified to 100 plus 14 times 0.8, and the final answer is 111.2 millimeter. So let's move on to the total extension after 15 cycles as 15. So the method of doing it is bracket 2 times 100 plus 14 times 0.8. Then it will be simplified into 7.5 times 200 plus 11.2, and the final answer will be 1584 millimeter. So next, we'll be going to the average extension per cycle up to 15 cycles. So average is sum of 15 terms, sum of the first 15 terms divided by 15. So our answer will be 105.66 millimeter. We move on to the final question, which is first cycle n when Tn is more than or equals to m. So the value of m for our group is 112 millimeters. So we can convert into 100 plus bracket n minus 1 close bracket times 0.8 more than or equals to 112. So this will be simplified into n minus 1 times 0.8 more than or equals to 12. Then we will get n is equals to 16. N is more than or equals to 16. So our final answer will be n equals to 16. So next, I'll be showing you the table for Tn and Sn for 20 cycles. And then I'll show you the graph of Tn against n and Sn against n, including line for m. So that's all from me. Thank you.
Hi, my name is Muhammad Aziz bin Padizi. My metric number is AA251486. So for this section, I will explain the calculation of extension using a geometric sequence. The extension increased by a constant ratio in each cycle, so a geometric sequence is suitable for this analysis. The first term A1 is 100 mm and the common ratio R is 1.008. The formula for the n term is Tn equal to A multiply R power bracket n minus 1, and the formula of the formula for the sum of the first n term is Sn equal to A bracket R power n minus 1. So for the first question, I calculate the extension at cycle 50 by substituting the value into the n term formula. T50 equal to 100 multiply bracket 1.008 power 40, which give 111.8 millimeter. This means the extension at the 50 cycle I get is 111.8 millimeter. For the second question, I need to calculate the total extension after 50 cycle. Using the sum of geometric series formula, the total extension at S50 is 1586.98 mm. So the total extension accumulate over 50 cycle is 1586.98 mm. So for the third question, I find the average extension per cycle. The average extension is calculated by dividing the total extension by the number of cycle. Therefore, the average extension per cycle I get is 105.8 mm. Finally, for the last question, I determine the first cycle when the extension reaches or exceeds the maximum limit. The maximum allowable extension M is 130 mm. Using the n term formula, 100 multiply bracket 1.008 bracket n minus 1 power n minus 1 greater than or equal to sin 130. After simplifying, I get that n minus 1 greater than or equal to sin 50.22. Since the second number must be a whole number, it is round up. Therefore, the extension first ascend the limit at cycle 60. So, this is the table for Tn and Sn for 20 cycle. This is the graph that I plot using a Excel for 20 cycle. The first graph is about Tn versus N for 20 cycle, and the second graph is about Sn versus N. It includes a line of maximum allowable extension, that is M. In conclusion, the geometric sequence model successfully predict the extension growth and identify the cycle at which the maximum limit is extended.
Hi, my name is Badara Aina binti Martan. My number matrix is AA252116. So now I'm going to discuss about comparison. The comparison shows that the geometric model predicts unsafe condition earlier and exhibits a faster growth rate than the arithmetic model. Although both start at an initial length of 100.0 mm, the arithmetic model increased linearly by 0.8 mm per cycle, while the geometric model grows progressively as the expansion rate depends on the current length. As a result, by cycle planning, the road length in the geometric model is significantly greater than in the arithmetic model. In terms of safety and performance, relying only on the arithmetic model may underestimate the actual risk, whereas the geometric model better reflects real conditions due to material fatigue that accelerates expansion. Exceeding the 112.0 mm safety limit could lead to servo engine damage and costly repair. So now I'm gonna explain that engineering results are influenced by factors such as operating temperature, material strength, design tolerance, and material fatigue, all of which affect thermal expansion and reduce the number of safe operating cycles. Higher temperatures and repeated heating accelerate expansion, while suitable material choice and sufficient design tolerance improve safety margins. To address this issue, engineers should select thermally stable material, apply effective cooling system to control temperature, and perform scheduled maintenance to prevent failure before critical limits are reached.
Hi, my name is Najwa and my matrix number is AA252131, and I will present the conclusion for our PBL project on algebra sequence. So in conclusion, the objective of this study was to model the thermal expansion of a pistol rod using both arithmetic and geometric sequence to ensure mechanical safety. The initial rod length, which is 100 mm, was compared to the maximum safe limit of 112 mm. Based on our finding, the arithmetic model, which assumed linear growth, predict that the rod will reach an unsafe length at cycle 16. However, the geometric model, which accounts for proportional growth due to material fatigue, reached the safety limit earlier. In terms of growth comparison at cycle 15, the extension was quite similar to both models, with 111.2 mm for the arithmetic sequence and 111.8 mm for the geometric sequence. However, the geometric model show a faster expansion rate over time. From an engineering perspective, this study highlights the importance of mathematical modeling in predicting component failure. Relying only on a linear model in high temperature could lead to dangerous underestimation. Finally, through this project, we learned how algebraic sequence can be applied to real-world engineering problems and the importance of choosing the correct mathematical model to ensure safety and performance in the future. Okay, that's all for me. Thank you.